meaning. So I'm interested in semantics, and for the purpose of today's talk, semantics is word meaning. So each one of us, as we learn about the world throughout our lives, develops a model of what words mean and what things are, and we carry that around in our brains. And so I'm interested in figuring out how you know what you know about the world. You might ask, well, why are you interested in semantics? And I think semantics and understanding semantics is key to several artificial intelligence challenges. A human-robot interaction can only be as good as the robot understands the human. And when it comes to higher order knowledge extraction, understanding what people meant when they wrote a particular sentence is incredibly important. And so semantics and understanding semantics at a deep level is also incredibly important. You might wonder why I'm interested in studying the brain. I think the brain is one of the few truly measurable ground truth semantic models. So each one of us has a sense of how the world works, what words mean, how things fit together. And each one of us stores it in our brains, and with brain recording technologies, we're able to access your internal stored semantic model. So to me, that's why brains are really interesting. Brains are also interesting, though, because we know very little about them, but they control so much of our lives. And so part of this research is motivated just by the importance of brains and how little we know about them. But there's also the fact that if we knew more about brains, we might be able to do more for people from a medical standpoint when it comes to treating brain injuries or planning brain surgery. If we understood better how the brain worked, we might be able to do those things better. And it's also true that if we understood how the brain did semantic tasks, we might be able to build algorithms to do those tasks better. This is the outline for today's talk. We're going to talk a little bit about semantics in the brain. Then we'll talk about semantics as we extract it from corpora, a large body of text. Then we'll talk about non-negative sparse embeddings. Then I'll talk finally about the joint model that I developed, text plus brain, non-negative sparse embeddings. To start it with first, we'll talk about semantics in the brain. OK, so what would it mean to have a good model of semantics in the brain? Well, we would like to know which areas of the brain light up in response to particular words or concepts. And if we had a model that did that, we would be able to predict the word a person is reading based just on their brain activation. But the problem with this is that there are tens of thousands of words in the English language. So there are far too many words for us to collect brain images for them all. And on top of that, people continue to make new words all the time. So for example, Twitter was not what it is today 10 years ago. And so semantic models are changing over time. And we need a way to adapt our models without having to collect new training data. So we also want to be able to predict for unseen words. So even though I didn't see a word during training, I want to be able to predict that word when I see your brain image for it. And in machine learning parlance, that means I want to be able to test on unseen classes. So we can't train a classifier for every word, for the two reasons we just talked about. There are too many words, and in addition, we want to be able to predict for words we didn't see at train time. So to get around this, we're going to do something a little different. We're going to train a classifier for features instead of for words. So features are things like, is it edible and is it alive? So we're going to train classifiers that can predict that, and from that, we're going to be able to predict words. So to make this concrete, I'll go through a little example. Let's say we lived in a world where there were only 3 types of things: your mom, pizza, and a golf ball. So if at train time you only see your mom and pizza, you would learn that your mom is alive but is not edible, and pizza is not alive but is edible. And then at test time, if I showed you a golf ball, you would be able to tell that a golf ball is not alive and is not edible because at train time you had seen both of those things. So in this way, even though you had never seen a golf ball during training time, you're able to tell what a golf ball is because you have trained on the features of the things that live in your semantic world. So this gives us the generalizability that we're after. Now we're going to be able to predict for words that we did not see during training time, because we're going to predict the features of the words rather than the words themselves. So what I'm actually saying is that semantics is equal to features. So word meaning can be composed of the things that are true and not true about a particular word. So measuring semantics we talked a little bit about, but we'll make it more concrete now. If I asked you to name for me some typical fruit, you might name something like an apple, a pear, or an orange. You probably would not name a tomato or a cucumber, even though those things are fruits, because we eat the part of the plant that has the seeds. They're atypical because they're more savory than sweet. So if we had two axes in our semantic world, whether something is found in salads and whether something has seeds, we would find our typical fruits on the bottom right-hand corner. They most often have seeds, except for maybe the seedless orange, and they're rarely found in salads unless it's a special salad. We would find our typical fruits on the top right-hand corner, atypical fruits, tomatoes and cucumbers, because although they contain seeds, they're more savory, so they're more often found in salads. We might actually find that our atypical fruits are closer in semantic space to vegetables than they are to their typical fruit counterparts. So this tells us something about fruit. It tells us that some fruit is more like vegetables than it is like typical fruit. So what I just explained to you was a very simple vector space model of semantics. A vector space model of semantics just gives each word a point in high dimensional space. So our dimensional space has only 2 dimensions here, and each word gets assigned a point. So for example, apple is the point 1, 0.3, carrot is 0, 0.8, and those points define the word's meaning by where it lives in semantic space. But of course, we lived in a world with more than just fruits and vegetables, so we need to be able to assign these semantic features in an automatic way, and in a way that can split up and distinguish between many different kinds of things. So we need a way to define the dimensions, like does it occur in salads and does it have seeds, in an automatic way, and assign the values for each one of the words in an automatic way. So this brings us to our second topic, semantics in corpora. So we're going to harvest semantics from a huge text corpus. Our text corpus is 16 billion words and 50 million documents. And I'm saying here that the statistics that we collect from this corpus are going to substitute in for the features that we talked about before. So now the statistics will be substituting in for is it alive and is it edible. So these statistics will come from word associations, so how often we see words near each other. Specifically, we're going to find these associations using the dependency parsed sentences in the corpus. So dependency parsing looks something like this. If I have a sentence like John hit the bouncy ball, the dependency parser will assign part of speech tags to each of the words. So here ball is a noun, hit is a verb. And then it will draw links between the words in the sentences that define the relationship between the words in the sentences. So for example here, ball is modified by the adjective bouncy, and John is the subject of the verb hit. So we're going to count the dependencies for the target word. And then we're going to end up with vectors that look like this. So John was the subject of the verb hit 1 time, so it gets a number 1. Ball was modified by the adjective bouncy 1 time, so it gets a 1 in that column. So what we end up with is a huge matrix where each one of the columns corresponds to one of these dependency features, like was modified by the adjective bouncy. And each one of the rows corresponds to a word. So this is a huge matrix. It's got 50 million rows and 50,000 rows and 1.25 million columns. So this is too large to work with practically, so we often do some dimensionality reduction, for example, SVD, to make this matrix more narrow so that we can handle it better at computation time. So this compressed matrix substitutes in for our vector space model, and it's going to define the points in space where the words live, and so there's semantic relationships between each other. And then, how are we going to use this to do anything with brain data? Well, what we're going to do is train a regressor for each one of the semantic dimensions. The regressor takes as input the brain data, and as output is going to predict one of those semantic dimensions, semantic features. And then at training time, we're going to train on n-2 of our training examples. And to test, we'll use the 2 held out words. For those 2 held out words, we'll predict 2 semantic vectors using the brain data as input and predicting each one of the dimensions independently. And then we'll have held out also the 2 true semantic feature vectors for those 2 words. And then our task is to choose the assignment of true to predicted feature vector that minimizes the sum of distances. So essentially, this task is trying to tell the difference between 2 words by choosing the best assignment of those 2 words to each other. So this is the typical pipeline. On the top, we do something with our corpus. The corpus comes in, we collect some statistics, do some dimensionality reduction, and out comes our vector space model of semantics. We'll use some of those rows in the second step along with the brain data to train classifiers and do word prediction, and out will come our prediction accuracy. Of course, what I said to you at the beginning was that prediction accuracy is only half of the goal. What we actually want to do is understand how the brain represents semantics. And we want to know specifically which brain areas light up for which words or word meanings. So let's say we train a classifier, it works really well. We know that for a particular brain area B, we can predict SVD dimension 12 really well. OK, so for an analysis, we'll go in and we'll find brain area B. Here's brain area B. Some of you may not know what brain area B does, but that's OK, because that's what we're trying to figure out. We're trying to figure out what brain area B is doing. And so since SVD dimension 12 works really well, is easily predicted from brain area B, they must have something in common. So let's look at the top scoring words for SVD dimension 12. Plan, E, engine, rock, vary. It's pretty hard to tell what these words have in common. So have we gotten any closer to our final goal of understanding how the brain represents semantics? I would say when it comes to predicting these SVD dimensions, we're still a long way. We don't know what it means that brain area B predicts this particular SVD dimension very well because we don't know what this SVD dimension is representing. So this brings us to non-negative sparse embeddings, which particularly try to tackle this goal of interpretability. So non-negative sparse embeddings, or NNSC, is a matrix factorization algorithm that takes as input all of our corpus data, which we'll call X. So each one of the rows corresponds to a word, and the columns are these corpus statistics that we talked about. And it's going to find a matrix A and D such that their product is approximately equal to X. So A and D share a latent dimension L that's much smaller than C. So we're making our dimensions smaller. We're doing dimensionality reduction. So we're going to use the vectors from matrix A as our semantic features, and we're going to do the word prediction that we talked about before, just like with the SVD matrix. Non-negative sparse embeddings look like this. OK, so our corpus data X is factored into matrix A times D, and we have a sparsity constraint on A, meaning that most of the values of A should be 0. And then this is the non-negativity constraint. And then we have a constraint on D so that D isn't made arbitrarily large while A is made arbitrarily small. And so while I'm telling you that X is approximately equal to A times D, I actually think it's slightly easier to think of X as being mapped onto the latent space A through some mapping D that we learn as well. You could think of it as X times D inverse is approximately equal to A. This just makes it easier to draw pictures later. So these sparsity and non-negativity constraints that we've introduced into this matrix factorization algorithm are the two things that are going to give us the interpretability that we're interested in. So interpretability, like we talked about before, for SVD is difficult. If you look at the top scoring words in some random dimensions of your SVD matrix, it's hard to see what the words have in common. But if we do the same thing for a non-negative sparse embedding, it's really easy to see what the words have in common. So the first dimension here, inhibitors, inhibitor, antagonist, receptors, inhibition. It's easy to see this is some sort of biology-related dimension. Noisy, adverse, leery, and unsympathetic and snotty. These are words you would not want somebody to use when describing you. This interpretability also gives us this really neat ability to create word definitions. So to create a word definition, we can choose a row from our matrix A, find the top scoring dimensions for that row, and then find the top scoring words for those dimensions. So if we do this for the word motorcycle, the first dimension has something to do with bikes. The second dimension is modes of transportation. The third dimension is cars, car-related things. And the fourth dimension is lawyers and stuff. So you can think that motorcycles are bike vehicle cars that are somewhat litigious, which is pretty accurate. Now we're moving on to the actual meat of this project, which was using text and brain data together to do this matrix factorization. So what I've told you so far is that people take written language and they use it to create some vector space model of semantics. And then they use that vector space model of semantics to tell them something about the brain by training classifiers or regressors on brain activity. What I'm suggesting instead is that we take written language and brain activity and use them both together to create a vector space model of semantics. And then we're going to use that same vector space model to help us understand brain activity. So the brain activation data that we used in this experiment comes from two sources. The first is fMRI, which you might be familiar with. fMRI measures changes in blood oxygenation in response to you using particular parts of your brain. It has great spatial resolution, but really bad time resolution. We also use magnetoencephalography data. Meg data has good time resolution, but really bad spatial resolution. And it measures the magnetic field caused by many of your neurons firing in the same direction at the same time. So these are two very different data sources. They have very different spatial and time resolutions, and in addition, they're measuring two very different side effects of neuronal activity. So we have 18 subjects in total, 9 in fMRI and 9 in MEG, disjoint sets. Each word was viewed, there's 60 words, and each one was viewed as a line drawing with the corresponding word. So for example, like this picture of the dog with the word dog. And there were 60 concrete nouns. And this data was not intersubject aligned in any way. So we did nothing to try to account for the fact that people's brains are different sizes, they're different shapes. We left everything in its native brain space, and our algorithm is able to use that brain data in that form to improve semantic embeddings. So this is the non-negative sparse embeddings that we just talked about. You take your corpus data X and you learn some mapping D that sends it into the latent space A. So X has corpus features as the columns and words as the rows, and your learned latent space A will also have words for rows. And some subset of those rows, A prime, will also have brain data. So we're going to incorporate the brain data like this. We're going to learn the brain data also has rows A prime. And the columns here will be voxels, or you can think of them as sort of time space points for brain data. So we're going to learn another mapping D superscript B that takes that brain data and maps it onto some of the rows of the learned latent space A. So that's what this looks like in math. Here's the original constraint that we talked about before, and the sparsity constraint. And here's the additional constraint that we're adding. We're asking that some of the rows in A also be able to explain the brain data Y using the mapping D superscript B. You have a question?
So what was the word in the brain data?
Pardon me?
Can you go back one slide? So what was the word here in the brain data?
So these are the 60 concrete nouns. So things like dog and... Any other questions? Uh-huh.
Does the language play any role at all? Like English or French?
In the, pardon me?
Does the language play any role at all, or do you consider only English?
Oh, I see. Yeah, OK. So for this study, we used only native English speakers. And we didn't specifically tackle bilingualism here, but in the past, it has been shown that people, even if they're bilingual and they hear words in their two different languages, their semantic representations are similar enough that you can do classification across language. So even though we're just using English here, you can think of it, it would probably be applicable to any language, as long as you had the corpus data to do the same sort of techniques that we're talking about here. Good? Are there other questions? OK. Oh, sure.
The first part mapped to A and A prime, or A?
Does the first part like X?
Yeah.
So X maps onto all of the rows. So A prime is a subset of A. So X maps onto all of the rows of A, and Y maps just onto the subset A prime.
So A prime is part of
A prime is a subset of A, yes. Other questions? OK, good. OK, so we're asking that some rows of A have to be able to explain brain data Y, and all of the rows of A have to be able to explain the corpus data X. We're going to keep the sparsity constraint on A and also the non-negativity, although I'm not showing it here. One important thing to note here is that we have only partially paired data. So if you use something like CCA, you would only be able to use the corpus statistics for the 60 words for which we also have brain data. But this matrix factorization setup allows us to use all of the corpus data for all of the words we know about even though we only have brain data for a very small subset of them. So the experimental setup is going to look like this. We're going to take one subject's brain data. We're going to use that subject to do the matrix factorization. And then we're going to use the vectors that come out of that learned latent representation to do word prediction for the remaining 8 subjects. So originally what we had talked about was we use corpus data to create a matrix A, and then we use that matrix A to do word prediction. What I'm saying we're going to do instead here is we're going to use one subject's brain data in the first step of the pipeline in order to do the matrix factorization. So we're going to get a learned representation A that depends on the subject. So for here, the subject is subject 1. Then we're going to use A prime, which depends on subject 1, and the remaining 8 subjects, subject 2 through 9, in order to do word prediction, and we'll get out as some measure of word prediction accuracy. So the results look something like this. On the y-axis here is the 2 versus 2 accuracy we talked about. On the x-axis is the number of latent dimensions I'm allowing A to have. So how wide is A? You can see as I increase the width of A, the prediction accuracy for predicting words from brain activation data is actually going down. So this is predicting on MEG data. So this tells you that as we increase the number of latent dimensions, what we might actually be seeing is that the matrix factorization is using those extra dimensions to overfit to the corpus data, rather than taking into account things that are common between brain data and corpus data. But when we include brain data, what we end up seeing is a much different pattern. As we include the number of latent dimensions, then performance improves. And here I'm showing you performance when I do the matrix factorization using either fMRI or MEG. And you can see, sort of irregardless of which brain modality I use to do the matrix factorization, the performance improvement is consistent. You can do the same thing testing on fMRI data. Again, the y-axis is 2 versus 2 accuracy, and the x-axis is latent dimension. And we see the same pattern as we increase the latent dimension. It looks like we might be overfitting to the corpus data, but as we include brain data, we actually see improvements in performance as we increase the number of latent dimensions. So I want to remind you of 2 things. First of all, fMRI and MEG are very different brain recording modalities, but it appears here to not matter which one we use. In fact, here the highest performance actually comes from using MEG and testing on fMRI. In addition, we didn't interalign subjects in any way. So we're using one subject's brain data to create the vector space model. We're testing on different subjects. We didn't do anything to try to get their brains to line up, and this still works. Well, the reason it works is because what we're interested in is the closeness in brain space. So if 2 words have very similar brain activations, they'll be close in brain space for a particular subject, and that will have to be borne out in the learned latent representation A. The vectors for those 2 words will also have to be close together. And it's those distances that we're using to our advantage here.
So can you comment on the standard errors?
So there's no statistical difference between the 2 modalities. So fMRI and MEG perform within each chance of each other here. But it is significantly better than the non-negative sparse embeddings.
Can you also comment about why 60 words, including 60 words in the optimization problem, affects what you learn over the 50,000 words?
So that's actually not what I'm claiming right now. What I'm claiming right now is that if we include the 60 words for a particular subject and then test on those same 60 words for a different subject, we're seeing an improvement. But I'll actually address your question a little later in the talk. Good? OK. So I've told you that including brain data makes vector space models that are better for testing on brain data. So maybe you're not surprised. I think you should be, because we didn't intersubject align, and fMRI and MEG are very different. But maybe you're not impressed. So we'll try another semantic task. So here we're trying to represent semantics using behavioral data. So what we did was we took 218 questions, and we asked them of mechanical Turkers for each one of our 60 words. So for each one of the 60 words, we asked them to rate on a scale of 1 to 5. Can you hold it in one hand? Is it alive? Is it bigger than a microwave oven? These sorts of things. And so essentially what we get is a behavioral vector space model of semantics for our 60 words. So we end up with vectors for each one of the 60 words, but instead of corpus statistics, they are the answers to these 218 semantic questions. And the question, we can correlate the distance in that behavioral space to the distances in our non-negative sparse embedding or the joint non-negative sparse embedding that includes brain data. So we have the same sort of graph set up here. And you can see that the models that include brain data are more significantly correlated to the behavioral measures of semantics that we collected in a completely independent way. So now we have two models of semantics that we've shown are more consistent with vector space models of semantics that include brain data. This is the final task that we did for this particular study, and it addresses your question. So brain data is really expensive to collect. It takes a long time, and it's, you have to put people on an expensive machine, and you have to pay to use the machine. We would prefer to not have to collect very much brain data if we can get away with it. And it's also true, like we talked about before, there are many, many words in the English language. We have no hope of collecting brain data for all of them. So the question is, can we use non-overlapping sets of words to train our vector space model and test our vector space model? And if we do we still see the same sort of performance improvements? This gets at your question, which is, are you seeing an effect on the remaining words for which you don't have brain data when you include brain data for just a small subset? So what we're going to do here is include only 30 of the 60 words during the matrix factorization. So then A prime here will be just those 30 words. But the other 30 words for which we withheld the brain data, we'll still get vectors for, but they were trained just using text data. And then in the second half of the pipeline, when we do the brain activation prediction, we're going to take as input the 30 words from the matrix factorization for which we did not include brain data. And we're going to test on those 30 words. So now we're asking whether or not the addition of brain data can percolate through and positively impact the vectors for which we don't have brain data. And so here on the x-axis is, oh, you have a question?
So how do you choose the 30 words? Are they like close to each other on the A matrix?
No, so I did that for illustration purposes. They're not close to each other. So the data that we had was 60 words, and they were distributed amongst 12 categories. So what I did was chose the 30 words to try to choose equally from each category. So it's as equally as possible between those 12 categories. OK, so on the x-axis this time, we have including all 60 words for training and including just 30 words for training. So we actually already saw these two numbers. This is testing on fMRI data. So you know that when we include all 60 words for training, using brain data, it is much better than just using the text alone. And so when we test on just 30 words, we're going to see a drop in accuracy because we only have half of the training data. So that's what we see here. So using just text only performs worse than using text only because we're only training on half the data. But when we include brain data, so we also see a drop, but we still see a significant improvement over the text-only model. So this shows that including even a small amount of data can positively impact the representation for words that we don't have brain data, for which we don't have brain data.
And the standard errors don't overlap?
No, so I'm not totally sure. I don't think so, but I would have to double check for this one. So I told you at the beginning of the talk that we're really interested in how the brain works and interpretability, and then I actually didn't talk about that at all. So this is the part where we come back to interpretability. So we're still doing this non-negative sparse embedding, but we're including brain data. So we can still look at the top scoring words for particular dimensions. Oh, sorry. And the neat thing about this particular algorithm is that we're going to learn this mapping D superscript B that maps the brain data onto the semantic representations in A. So now we're going to actually look at that matrix DB and see which parts of the brain are lighting up for particular semantic dimensions. So for a particular dimension in subject 3, the top scoring words were bathroom, balcony, and kitchen. And we see high activation in a part of the brain called the fusiform gyrus, which is known to be associated with place area words. For another subject, we see parlor, cafeteria, and lounge. And we see activation in the same brain area, fusiform, also associated with place words. Another top scoring dimension, buffet, brunch, and lunch. So these are food-related words. And we see activation in gustatory cortex, which is related to eating and tasting. Dimension with top scoring words, ankle, elbow, and knee. We see high activation in pre and post central gyrus, which are brain areas related to motion and touch. So in unsupervised way, what we ended up with were mappings from semantic dimensions that are interpretable onto brain areas that we knew had something to do with particular semantics, and that they're consistent with what we had already found in the literature. Uh-huh.
So are these like cross-subject or just like this subject?
This is just one subject, but I am showing you examples from 2 subjects here. But I went through these by hand and found these mappings.
So for example, this word very merged. You have shared 60 words across like 9 subjects.
Right.
So are these like 9 subjects have the similar pattern or just like one?
So this is just one subject, but remember that these vectors are more useful for doing the prediction tasks that we talked about than the vectors that don't include brain data. So there's evidence to think that these representations are consistent across people, although I'm not actually showing you the mappings onto other people's brains. Are there other questions? Okay. So I told you today that brain data can create semantic models that are better for prediction of words from other people's brain data, as well as are more correlated to measures of semantics developed from behavioral data. They work even though we didn't do any intersubject alignment, and they work even though fMRI and MEG are very different recording modalities. And they take advantage of the fact that we have a huge amount of corpus data, but only a very small amount of brain data. Thanks very much, guys. Are there any more questions? Sure.
So while you're using dependency word representation,
Oh, okay. So in a previous study, we found that the dependency parsed features were better for doing prediction on brain data. So that's why we use those.
And on your measure prediction part, is it true that we only have not vector that comes with all the measures of A and no consequence that comes with our
Yeah.
we have an intuition idea of what
Right. So the idea here was that D is like a dictionary, and you're asking you're telling the rows of A that they can only choose a small number of elements from D, the dictionary. We're essentially asking them to represent the brain data with very few sort of like dictionary elements. Does that make sense? I think you could probably play around with this non-negativity on D or sparsity, but the way of thinking about it is that they're these like dictionary elements. Does that make sense?
Yeah, have you ever tried, for example, without this constraint, without it?
So I've tried it without the non-negativity constraint, and that actually seems to work as well, and also maintains this interpretability. So I think the interpretability is really the sparsity is most important for interpretability. It's not so much the non-negativity.
Sorry, so just following up on that question. So for a single dictionary element, a semantic component, there's lots of zeros in the mapping of voxels.
There's lots of zeros in the latent representation A, but there's no constraint on D except for that it's unit length.
Okay, so it's not like sparsity among the voxels.
No. Yeah. But yeah.
When you're saying that certain kinds of words, a particular dimension in a vector predicts certain kinds of words better, do you mean that the value of that dimension is particularly high for the word vectors of those words? Or what exactly does it mean to say that this predicts those words better?
Do you mean at the beginning where I had the example of brain area B and SVD dimension 12? Or do you mean?
Yeah, I mean, but how do you say that a particular dimension predicts a word better?
Oh, so what I'm actually saying is that particular brain areas can predict particular elements of the vector space model well. And from that, you will assume that you can pick the words out well. You can distinguish between words. But I'm not actually saying that there's I'm not making any claims about the fact that if we predict a particular semantic dimension well, we can predict the word well. But, I mean, the words are separable in the semantic space. So if you do a good job of predicting the semantic dimensions, you will be able to do a good job of telling the difference between words, if that makes sense. Yeah. Jesse?
Can you just explain a little more explicitly why the constraints you imposed on matrix factorization make the model more interpretable? Is that just because you're assuming there's some underlying true factorization that you're capturing better when you regularize or something like that?
What's the
intuition behind it being more interpretable? So I think that really comes just from the sparsity. So we're saying you choose the 5 or whatever most important things for representing this word. You only get 5. So choose the 5 most important things. And that causes the matrix factorization to have to put weights on the 5 most important things for representing a dog, for example, rather than going down the line and sort of overfitting to the corpus data. Does that?
Well, I mean, in the previous model, you also were picking out the top 5, like you were picking the top 5 words for a dimension, right? So like, it's not like there was no way of correlating the dimension against the word that. You're saying that in defining the dimension, it required the most relevant.
So when I'm talking about interpretability, what I'm doing is comparing SVD to non-negative sparse embeddings. And there we looked at a few examples. We're looking at the top 5 scoring words in particular dimension. Doesn't tell you anything about the dimension. So what I'm saying is in matrix factorization, I mean, there's a big jump between SVD and non-negative sparse embeddings, but non-negative sparse embeddings give you, with the non-negativity and the sparsity, give you the interpretability that we were after. But I'm not saying actually that there's a difference in interpretability between the joint and text-only model.
Any intuition why the NNSC parsing word notation works better for the
So we compared it to things like word co-occurrence in the same document. And I just think it's a better, more local measurement of semantics. So I think it has higher specificity.
For incorporating behavior features, do you add those features onto the frameworks of features or for each word, or do you represent those features separately and do a classification for each of those features?
So we did it completely separately, but you're right that we definitely could include it in the matrix factorization. OK, thanks, guys.